In our recent video, we just went over the 4 principles of experimental design: comparison, random assignment, control, and replication. We went over their details and the reasons why we need each one to make a good experiment. So let's go through an example together that looks at some of these principles. So in a previous example, a school set up an experiment in which 500 geometry students were randomly assigned to take a course online or with lectures by a teacher. The same teacher was used for both courses, and both met for 58 minutes per day. At the end of the year, the success of each program was measured by students' scores on the geometry final exam, which was the same for both courses. So we're going to go through here. We want to explain how this experiment used comparison, explain the purpose of randomly assigning them to 2 treatments, name 2 different variables that were controlled in this experiment, and then why it was beneficial, and then how did the experiment use replication, and then what is the purpose. So I would actually encourage you, if you wanted to pause this video and just take some time to either think through these answers, jot some thoughts down, and then when you've given it some good thought, unpause and we can kind of see how your thoughts compared to the answers. So in the first question, explain how this experiment used comparison. Well, pretty simply enough, the researchers used a design that compared 2 treatments, an online course and a teacher-taught course. So that was the comparison. They had 2 things to look at. They didn't just say, is the online course effective, and only do the online course. They compared it to this also teacher-taught course. So that's how comparison was used. Part B, explain the purpose of randomly assigning the students to 2 treatments. So random assignment helped ensure that the 2 groups of students were roughly equivalent at the beginning of the experiment. So to avoid having to go through and be like, okay, well, I'm only going to pick students who are highly motivated, or students who have high GPAs, or students who have an affinity for math. Like, no, the fact that you did random assignment was helping to ensure that the 2 groups were roughly equivalent, meaning they were both, heterogeneous in their characteristics at the beginning of the experiment. Part C, name 2 variables that were controlled in this experiment, and then why it was beneficial to control these variables. So, the experiment used the same teacher for both courses. Each course met for the same amount of time. And then also, here's another one, both courses used the same final exam. So by keeping these variables constant, it helps reduce the variability in the response variable. So you don't have to be at the end like, oh, well, did they do better because it's online or because of the teacher that taught it? So teacher doesn't have to be a confounding variable here because the teacher was the same for both. Same thing with the amount of time that they met and then the exam that was given. So these are things that you can control. Now, obviously, there are other things that you cannot control, right? You can't control, how much time students spent studying for it. You can't control whether or not they have experience with online courses, etc. But that's why the random assignment part was so crucial, is because that made sure the groups were equivalent enough that even though you can't control for some of those things, the random assignment kind of took care of that. And then control, obviously, the things you can. And then part D was explaining how the experiment used replication. So there were 250 students in each treatment group. So replication, remember, doesn't mean to do it again. It means using enough subjects. So this helps ensure that the difference in the scores on the exam is due to the type of the course and not due to chance variation in the random assignment. Okay, so that's our purpose. So they use replication by using 250 students, right, which is a good number. And then the purpose of replication here is to make sure that the differences was because of the course and not just because of chance variation. Wonderful. All right, let's look at a little bit more on how to design some experiments. One of the most popular and easiest ways to design an experiment is using a completely randomized design. In a completely randomized design, the experimental units are assigned to the treatments completely by chance. Right? So there's that random assignment again. Some things about completely randomized design. It doesn't require that each treatment be assigned to an equal number of experimental units, but it is nice if you're able to make it happen. Some things to note, there may be more than 2 groups because there may be more than 2 treatments. In our first video for the experiment section, we looked at how do you figure out the number of treatments, and you looked at the number of factors and the number of levels, and you did a little basic math there to figure out the treatments. So if you had 6 treatments, then you would have maybe 6 groups or more. Now, some experiments may include a control group that receives an inactive treatment or maybe an existing baseline treatment. Now, note for AP purposes and for our tests and quizzes, simply drawing a design of your experiment is not going to receive full credit. You also have to have a written description. Another caution, if you're asked to describe a completely randomized design, stay away from the whole flipping coins as your method of randomly assigning units to groups. If you want more details on why you should avoid using that as your chance process, you can look in your textbook on page 284. Here is kind of how our completely randomized design is going to start. So you always start with your units. Okay. From there, oops, wrong way. From there, you're going to randomly assign them in some way into groups. So random assignment can be done using slips of paper. It can be done using technology. It can be done using a random digit table. But you need to randomly assign them, not just say, hey, I'm going to split them in half. No, you need to specifically describe how you would randomly assign them in detail. So don't just say, I'm going to use a random digit table to assign them. You need to fully explain it out. Just like you did when we did simple random samples, explain how to use the random digit table. Same deal here, explain in detail. And this is a part students sometimes kind of mess up. They jumped right from random assignment into treatments. But you don't do that. You jump from random assignment to groups, and then you need to put the groups with a treatment. Okay, so there is the step where first they're in a group, and then that group gets a treatment. Now, in this one that I've outlined, there's just 2 treatments. And then finally, don't forget this part because this is crucial, after you've randomly assigned, put them in groups, the groups are assigned a treatment, you have to wrap up your experiment. So compare your results, whether that be looking at their average SAT scores between the 2 groups and then comparing the 2 groups to see how they did, or measuring the weights of things and seeing how they compared. So you need to have that comparing results at the end, and you need to write that out in your design. Here's an example. A Harvard researcher was once conducting some experiments at Western Electric's Hawthorne Works to see if certain changes in conditions would improve worker productivity. In one part of the study, a group of workers was provided additional lighting and was compared to a group with no additional lighting. The group with additional lighting showed significant improvements in worker productivity. We want to explain why it isn't reasonable to conclude that the additional lighting is effective for increasing worker productivity based on this study. And then we want to go ahead and, in order to test the effectiveness, we're going to recruit 20 similar companies that have agreed to have employees participate in an experiment. We want to write a few sentences describing a completely randomized design for this experiment. So the first part, why isn't it reasonable to conclude that's effective? Well, it is possible that the group who received the additional lighting improved because they knew they were being measured, not because of the additional lighting. Here's a fun little note. You don't have to write this down, but I thought it was a fun little fact. This phenomenon is now commonly known as the Hawthorne effect. You can Google it. But it describes how worker productivity can increase simply because they know that they're being measured on it. So perhaps, what we did say on the problem, they were looking at if it would improve their productivity and they knew they were being measured. So let's describe how I would design an experiment, a completely randomized design, mind you. So we want to number the companies from 1 to 20. You can use a random number generator to produce 10 different random integers from 1 to 20 and increase the lighting at the facilities of these companies with these numbers. Leave the lighting as it is for the remaining 10 companies and then compare the increase in worker productivity between the 2 groups. Again, you could have used a different method. It didn't say how to randomize them. So if you wanted to do 20 slips of paper, and 10 of them said increase and 10 of them said stay the same, divvy it out that way, or using a random digits table. That's also another option. Here is another example that I want you to literally pause this video and do it on your own. So a health organization wants to know if a low-carb or low-fat diet is more effective for long-term weight loss. The organization decides to conduct an experiment to compare these 2 diet plans with a control group that is only provided with a brochure about healthy eating. 90 volunteers agree to participate in the study for 1 year. We want to outline a completely randomized design and then describe it completely. So again, the diagram doesn't give you the full credit. The diagram can help you though. All right, hopefully you've paused and now we can take a look at our design that we've described. So we would use 90, in this case, equally sized slips of paper. I'm going with the slips of paper route here. Label 30 of them 1, 30 of them 2, and 30 of them 3. Mix them up in a hat and have each subject draw a number without looking. That number then is going to be the group that they're assigned to. And then each group is going to get a particular treatment, which I'll show you in the diagram. And then at the end of the year, the amount of weight loss will be compared for the 3 treatments. So notice how I didn't just say, group, if you have 1, you're going to be low carb, and if you have 2, you're going to be low fat, or whatever it is. I'm saying that's the group they're in. So as far as a visual, you start with your 60 subjects. You have your random assignment, which randomly puts them in 3 groups of equal size, groups 1, 2, 3. From there, keep going the wrong way. From there, we have our 3 treatments, low carb diet, low fat diet, and then just that's the control group. It's still considered control even though they're getting a treatment because it's kind of like the baseline versus low fat, low carb. And then finally at the end, you compare the weight loss results. Wonderful. In our next video, we're going to talk about another type of experimental design called a randomized block design, and then a very specific example of a randomized block design that's called matched pairs design. So that's going to be in our next video.